Hello. So it's a pleasure to introduce Evanthia Hatziminaoglou from the ALMA Regional Center at ISO in Garchin. Evanthia is visiting us for a couple of weeks. She was postdoc here some years ago. She worked on her PhD in Toulouse, working on quasars. After that, she moved for her first postdoc to ISO, working on the ISO imaging survey. Then she came to the IC at the time of the first SPIRE surveys. I mean, we were working at that time on the SWIRE SPIRE survey, the widest and deep at that time SPIRE survey, and also in the instrument control center of the HERSCHEL SPIRE instrument. And after that, she moved to ISO to work at the Virtual Observatory Center facility at ISO. And in 2010, she moved to the ALMA Regional Center in ISO. And she is the coordinator of a very large group of people spread all over Europe in the different nodes of ALMA, the ALMA Regional Center nodes. And she coordinates the support of those astronomers who support any of you working with ALMA data in Europe. Apart from that, she's very active in science, and she's going to talk today on observations of quasars, optically bright quasars selected from Sloan with the ALMA Compact Array. So please go ahead.
Thank you very much for having me here. It's always a pleasure to come back. So what I'm going to talk to you about today is a very, very recent work. In fact, we just received the referee report and it was very favorable, so this all is going to be published very soon. And indeed, it's about data we took with the ALMA Compact Array, so the array that is made for not very high resolution, but large structures, on bright quasars that we have also observed with HERSCHEL. So just to set the scene, I know this is very basic things, but I want to make sure that when we talk about AGN, we all talk about the same things here. So active galactic nuclei all share a variety of properties that are quite unique, though, to these objects. So first of all, they reach very high luminosities. They can reach easily 10 to the 48 ergs per second. They have very small emitting regions, very strongly evolving luminosity function with redshift. Their emission covers a very large fraction of the electromagnetic spectrum. So in fact, we can observe them pretty much everywhere. And they're highly variable. So this is from a recent review paper that it was the outcome of a conference we had last year at ISO. It was on the multi-wavelength properties of AGN. And this is just a schematic to show you how the emission of an AGN, of a typical AGN, looks like. So in blue is the optical UV, the typical blue continuum with a big blue bump here. And there is X-ray emission from the hot corona with a reflection component at the soft excess. And there is also dust emitting at mid-infrared. Well, the rest is of no importance here, but this is a very typical emission pattern for any type of AGN. And basically, we want to oversimplify. This is what a normal galaxy looks like, if such a thing exists, and this is what an active galaxy would look like. And this is two very different beasts, in fact. So the structure of the AGN is, we think it looks like that. So basically, there is an accreting black hole in the center and materials falling through an accretion disk that forms around it. Surrounded by a broad line region. Broad emission lines are very typical for at least an obscured AGN, and then further out there is dust in some configuration that's often referred to as torus, but not necessarily, and on top sits the narrow line region with typical narrow lines for all AGN. Now this is a schematic, of course. The reality is probably much more complicated than that, but I think this is enough to set the scene here. However, even though we seem to know a lot of things about AGN, there is also very many things that we still don't quite know, and actually simple things like the physics of the emission lines, for example, or the composition, geometry, and morphology of the dust, the drivers of the relativistic jets, the role of the spin of the supermassive black hole, and various other things. And when we go to the population of AGN, to the demographics, the questions are even broader and even more important, if one can distinguish. And this is what is actually the complete census of AGN when looked at all wavelengths. How does the cosmic history of the black hole accretion traced by this population compare to the history of the star formation in the universe? What is the physical connection between the evolution of the black holes and that of their host galaxies, and what are the triggering mechanisms? So these are really very basic questions that one would have hoped that we would have answered 55 years after the first quasar discovery. However, we're still far from it, and sometimes for us that work on AGN, we have a bit the feeling of, we're doing this. We're looking a little bit of the puzzle and we're giving a little bit of the answer. In fact, I think we're still quite far from really grasping what we are dealing with. So going back to all these questions, the two I would like to address here are this one. So basically, what is the physical connection between the evolution of the galaxy and the AGN it's harboring, and what is triggering these very energetic effects? So a few background stuff here. So first of all, supermassive black holes are now believed to exist in almost all galaxies. Every galaxy that respects itself has to have a supermassive black hole in it. And accretion into supermassive black holes and star formation are very often observed to happen concomitantly at all redshifts and out to extremely high star formation luminosities and AGN luminosities. So this is a figure from a paper from James Aird in 2015 that shows that supermassive black hole growth and galaxy growth actually broadly trace one another. So here you see the star formation density. In orange is the infrared, in blue is the UV ones. They match pretty well one another over the age of the universe, or the redshift here. And in black is a scaled black hole accretion density curve, and you see that really the two things broadly match each other over the entire history of the universe. So there are some facts. Already this tells us that something must be guiding this concomitant, this evolution of the two very distinct processes. And the first hint comes from the relatively tight M sigma relation. So this is the relation between the mass of the black hole and that of the velocity dispersion of the stars in the bulge of the galaxy. And so basically, this quantity, the mass of the black hole, is of course driven by the AGN activity. More the AGN accretes, more the black hole grows. While the velocity dispersion is actually dependent on the potential energy of the system, or in other words, the mass of the galaxy, which is driven by the star formation. Now the question is, how can such events that happen in so different time scales and so temporal and spatial scales affect one another, especially given the difference in sizes? So when we compare where this happens with where this happens, the difference is between that of a grape and the size of the Earth. So it's really very, very different scales we're talking about. At the same time, the M sigma relation is also trying to tell us something else. Now remember that for a self-regulated supermassive black hole growth, what you require is both a lot of fuel supply and the growth of the bulge in such a way as to deepen the potential and to sustain very high electron accretion. Otherwise, the system will either self-regulate or starve. So something that can ensure both these things happening is major mergers. So major mergers ensure that both a large fraction of the galaxy mass is added onto the new bulge, which is formed after the two systems have merged, and at the same time it provides a mechanism that will bring material into the sensor in time scales that are much shorter than the dynamical time. And this is what you need to bring the material and make sure the black hole can eat it. So according to the models of Hopkins and Hercules from about 10 years ago, this of course are expected to be dominant, this mechanism at a redshift of 2 at the cosmic noon. And while at lower luminosity AGN, that needs much lower fuel supplies, this mechanism is not really necessary because they can also be triggered by secular processes that require, and also require much less material to feed the black hole. So they found that the division magically occurs somewhere between, somewhere around 10 to the 7 solar masses, which is also the division roughly between quasars and Seyfert galaxies. So on the observational side, people have already tried to see what the role of the major mergers is in samples of AGN, not necessarily related to AGN that actually also actively form stars, but to the whole AGN population. So examples of such studies are the one carried by Mulani et al. A few years back in the Herschel survey, where they selected, so this is X-ray selected, AGN of intermediate luminosity of 10 to the 42nd to 10 to the 44th erg per second. And they found that about 80% of those reside in the galaxy main sequence, so they are not really particular in any way. And most likely are driven by secular processes. When Tracer et al. Sort of extended this study to, again, X-ray AGN, but with much higher luminosities, they found out that about 10% of this most luminous AGN are actually connected to major merger events, and this corresponds, in fact, to about 50% of the total mass growth, so they are the bigger beasts in the picture. And the rest, again, they conclude that they are driven by secular processes. Now, both of these are X-ray selected AGN, mostly obscured. There is a very recent study by Hewlett et al. In 2017 that actually went and checked unobscured AGN, so type 1 AGN, with luminosities between 10 to the 43rd and 10 to the 45th ergs per second, so quite bright, not the brightest, but relatively bright. They did find that the merger rates increase from redshift 0.5 to 2, as is expected and predicted also by the models, but they found no relation in the merger rate with respect to the accretion luminosity. So whatever these people found, they could not confirm. But they found, they said, a global 15% of AGN residing in merging systems at this redshift. So the two questions I want to tackle here, which I mentioned before, are of course related to one another, but they're also related to the far infrared measurements, and especially to Herschel, because this is where we derive the star formation rates and all the information we have on these events for the past, 8 years now. So Herschel has a major contribution in our understanding of star formation in general and in star formation in AGN in particular. So about 2 years ago, I gave another talk. So those of you that happen to remember, you can have a nap now, because I need to remind you of a few things here, because really everything is a part of the same big complicated story. So what we did back then is that we went and checked in the large Herschel fields which Sloan quasars from the data releases 7 and 10 were individually detected by Herschel, not stacked, but had individual fluxes at 250 or 350 at or above 3 sigma. And we checked the large Hermes fields and also HERS, which is basically stripe 82, and Helms fields. And using a matching radius of 5 arc seconds, it's quite conservative, but the simulation have shown that using this matching radius, the sample is quite clean. There are no spurious detections inside. We ended up with a sample of 500 quasars that were individually detected by Herschel. So these were very bright optical quasars, Sloan quasars, that at the same time have a lot of star formation happening in their host that ensures these very bright fluxes in the far infrared. So this is the distribution of the sample. So in red is the quasars coming from DR7, in blue DR10 that was optimized to find high redshift quasars. So the total sample covers quite a good range of redshifts, so it goes from 0 to almost out to 4. And these are the Herschel fluxes. In blue, the 250 micron, so peaking at around 45 micron. In green, the 350, and in blue, in red, the 500 micron. So these are moderately bright far infrared emitters, but this, as I'll show later, they correspond to quite high star formation rates. So for these quasars, we found a detection rate by Herschel of about 5%. So these are really extreme cases. And this is also confirmed by other studies, similar studies done in the H-Atlas fields that we do not include here. And they found also the same rate, 5 to 8% of individual detections. So we are quite compatible. And for all of these objects, we have ancillary data, namely UGITS and VHS, so covering the near infrared, as well as WISE. So adding Sloan to these points and to the SPIRE points, we had a very good sampling of the SED that helped us do an SED fitting and decomposition and derive the contribution of the AGN and that of the starburst in the various places, and also calculate the star formation rates from this. So as I said before, these fluxes in these redshifts correspond to objects that are very, very infrared bright. So these are all Ullrichs in a sense. They are all above 10 to the 12 solar luminosities. And this translates to star formation rates that are peaking at around 1,000 solar masses per year. So if these things are real, these are really forming stars like crazy. And these are in the hosts of very, very bright quasars. So this is very remarkable, in fact. So in this work, what we wanted to do is confirm or refute whether the star formation rate correlates with the properties of the AGN, because there is all this... the basic and simple idea is that if everything depends on the amount of available material, the two should correlate. You have a lot of material to form stars, you have a lot of material to form to feed the black hole. Therefore, you should see a correlation. However, what we found here is that the star formation rate indeed increases by a factor of about 8 from redshift 0.5 to redshift 2, which is similar of galaxies in the main sequence. However, the star formation rate remains constant within redshift beams. So we cut in, okay, very large beams, but still, if you take here, this is about 1, 2, and above 2, there is no variation of the star formation rate with the accretion luminosity. There was also no dependence on the black hole mass, and this is even more surprising in a sense because, as I said before, everything scales with the available material, and one would expect at least to find some dependence of the star formation rate with the black hole mass, but we didn't find anything. We also didn't find any dependence of the star formation rates with the Eddington ratio. So these are all very bright quasars, creating at Eddington ratios at or above 0.1, and still everything is quite flat here. So no dependence on how efficient of the star formation rate on the efficiency of the accretion. So this was quite surprising. Still, these objects are not representative of the whole quasar population because they're really very strong star formers, but they were objects that were very, very intriguing, and we really wanted to figure out what is happening. So this work told us that for these objects, that again are the exception and not the rule, there doesn't seem to be any relation between accretion and star formation. So we set out to figure out whether these star formation rates were real, because that would be an explanation to why we find these things. If they were wrong, then okay, maybe we could explain why we don't find what everybody else is finding. So this is the question we set out to answer, and for that we applied for ACA standalone time with the cycle 4 delta call with ALMA. That was about a year ago, this call. And what we did is we selected from this sample of 500 quasars objects that were not lensed. They were all radio quiet. We imposed a estimated, based on the SED fit limit cutoff at band 7, so 870 micron at or above 18 millijansky, and try to not go very high in declination to avoid shadowing problems, because the ACA antennas are quite close to one another, so if you go very low, they will start covering one another. So we ended up with 28 quasars, no other cuts, all between redshift 2 and 4. In fact, as it turned out, while I was selecting the sample, I made a mistake somewhere, so this condition in fact does not apply, so I ended up with a sample that is much more representative of the total sample than I thought, so I'm actually quite happy about my mistake. So you can forget about this line here, but this was the original intention. So the sample of 28 has this median property, so the redshift is between 2 and 4 with a median of 2.67. They are moderately bright at 250 micron, again individually detected. Very large star formation rates, all above 1,000 solar masses per year, estimated based on SED fitting, of course. Quite bright also, accretion luminosities above 10 to the 46 error per second, and very, very bright in the far infrared, of course. So we applied for ACA band 7 continuum, so 345 gigahertz or 870 micron. This is a typical resolution of about 4 arcseconds. And we got on average 40 minutes per source in this range, depending on the brightness of the source, or estimated brightness of the source. And as it turned out, all of the sources were detected at or above 5 sigma, apart from one that was a 3.5 sigma detection. And in fact, 18 out of the 28 were detected at above 9 sigma. They were really very, very bright things. And all of them were unresolved. So this is the data. So here et al. Includes Ismail, of course, because we've been doing this work together. And you can see interesting. So first of all, if you compare the detections with the beam, you will find out that what you see is actually the beam. And this is all. So they're point-like as we expected. Another thing is that most of them are single sources. There are 6 of them that break into 2 counterparts. So, for example, this one is a blend. In fact, we cannot resolve the 2. This is a double source. And another 3 of them have 3 counterparts, like this one. What else? I can't see very well from here. Well, I'm sure you can see them better than me, but 3 of them have 3 counterparts. And we're talking about counterparts inside the SPIRE beam, right? So the SPIRE beam is 250 micron, has a full width of maximum of 18 arcseconds, so it's a really big thing. So we wanted to see how many objects contribute to the 250 micron flux. And to my surprise, at least, well, in the majority of cases, it was that object, the quasar itself. So we checked, of course, since we had all this ancillary data, to see whether some of the counterparts we saw were visible in any of the other images, and they were not. None of them were. So here's an example of an isolated source. So this is a single quasar. This is SDSS. This is UKIDS. This is WISE 3.6. This is SPIRE 250, and this is ALMA. Perfectly point-like, isolated on all images. Second example is one that is here. Okay, this is quite far away. Doesn't matter. So single, 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 then it also detects 250, and then suddenly on the ALMA thing, a second source appears that you do not see it anywhere else. So the sizes here are the same and all center of the same coordinate, right? The third one is an example of a triple source, where again, you don't see anything in any of this, all the way to the, well, near infrared. And then suddenly you start seeing things, but you cannot really resolve them on Spitzer, and then when you go with ALMA, you see that this thing is resolved into 3 different counterparts. So, again, such objects we have 3 out of 28, such objects we have 6 out of 28, and such objects we have, how many? 19 out of 28. So, we wanted to check whether there is any correlation between the flux of the source and the multiplicity. And this is now the 500 micron flux of each source as a function of the multiplicity, or right the other way around. And in fact, okay, we don't see any trend. Okay, the only thing we can say is that the objects that have 3 counterparts all fall right in the middle of the flux distribution, but this really doesn't say anything. So at first sight, there is no really relation or correlation between the multiplicity and flux. Now, regarding the astrometry, we want to make sure, of course, that you know, what we see comes from where we think it comes. So this is the original separation between the Sloan and the SPIRE coordinates. As I said, we cut at 5 arcseconds, so of course the distribution is below there. And this is the separation between the SDSS coordinates and ACA, and SPIRE and ACA. So 22 out of the 28 objects, 80% in fact, regardless of whether they had 1 or more counterparts, have their optical and ACA counterparts really almost superimposed, so at separations below, well below 1 arcsecond. 4 single objects have their ACA counterparts closer to the SPIRE centroid rather than the SDSS, and also 2 of the multiple ones, and I will come back to that later. So we checked on other images to make sure that the coordinates were correct, and the offsets are real, which means that the flux for this object might very well be coming from a companion and not the quasar itself, but I'll come back to that later. So regarding the flux distribution, so the total, so for every single source we detected inside the SPIRE beam, you can see that the distribution is bimodal. There is a peak. There is a peak at faint flux at around 3.5 millijansky, and another peak at around 8 millijansky. And so the big peak, the bright peak, is dominated by the primary source. So by primary, I mean the quasar, basically. And the faint peak is dominated by the secondary source in this case. In red, you can see the sample pointing. So for each SPIRE beam, the sum of all the counterparts. And the median flux of our sample is about this 7.8 millijansky. So instead of asking whether the star formation rates are real, because they seem to be, we should ask rather whether the multiplicity rays we find are real, given that the ACA resolution is not ideal for such a work. It's about 4 arc seconds. In fact, the beams were 4 by 3, more or less. So work done on HERSCHEL, on the HERSCHEL catalogs by Scudder et al. A couple of years back, so excluding all the galactic objects, or taking all the extragalactic population. They did some statistical studies, and they found that sources that are fainter than about 45 millijansky basically require one counterpart to reproduce the full flux at 250 micron. Sources that go above that, so much more brighter, they required at least 2 sources, and often a third one to recover 100% of the 250 micron flux. In other words, sources that are fainter than 45 millijansky should be single, and sources that are brighter should be multiple, according to this study. So this is the distribution of fluxes in the original sample of 500 quasars. And this is the distribution of fluxes in the sample of 28 quasars. So according to this, few should be single, most should be multiple. However, what we find is actually the exact opposite. Regardless of their flux, we find consistent 70% single counterpart rate, or 30% multiplicity. So we tried to do the equivalent of this plot. It's difficult to do, but this is the, again, 250 micron flux over the fraction of the contribution to the 870 flux per object. And we found, again, most of them are single, and the rest are well above half. So really, we cannot confirm what Scudder et al. Has done. However, there is a caveat when comparing the two. We're not necessarily comparing the same type of objects. So Scudder et al., they took the entire extragalactic population. We are focusing on very bright optical quasars with very intense star formation. So these are objects that are very go through a very specific phase in their lives. So this might be one of the reasons why we don't find the same thing. So there have been some studies, recent studies with ALMA on the multiplicities in sub-millimetre sources, not necessarily quasars, but sub-millimetre sources. The first one of which was with a sample of 126 sources from the extended CDF south field observed with HERSCHEL. Later on, they went and observed these objects with LABOCA. The beam of LABOCA is very comparable to that of the 250 micron HERSCHEL, so it's a very comparable study in a sense. Again, in band 7, continuum, but with a full array at a resolution of 1.6 arc seconds. So this was all cycle 0 data. So there was actually the first survey-type project ever observed with ALMA. The median flux of their sample is quite similar to ours, a bit fainter, but quite similar. And they found a multiplicity rate between 35 and 50%. So these are the objects. This is the LABOCA beam. And here you see the various objects and the multiplicity rate. So this is really very marginally comparable to ours. I would say they are, well, they are compatible within 2 sigma, let's say. Then Busman et al. Later on went and selected 29 dusty star-forming galaxies in the Hermes field. So again, HERSCHEL selected objects. Again, as for band 7 continuum, but at much better resolution, so 4 times better resolution than the previous study. Their sample was much brighter, however, so it's twice as bright as ours and that of Hodge. And they found a stunning 80% multiplicity rate. Okay, and the counterparts are separated typically by about 1 to 3 arc seconds. So here you see the SPIRE beam. These are the SPIRE contours, and these are the part of their sample. So definitely 80% does not compare at all well with what we find, but then again, this is much higher resolution than ours, and also most likely different kind of beasts. They also noticed that they don't comply with Hodge et al., so they took the images of Hodge and smoothed it to their own, actually smoothed their data to the Hodge resolution, and they found a 55% multiplicity, again marginally compatible to the previous study. So again, we're not really comparing same things here. This sample is brighter than ours, than that of Hodge. The resolution is much higher. The objects are possibly of a different nature, but this is indicative of what people have been doing with this, such studies. A study that is much closer to what I show here is that a recent one that Trachtenbrot et al. In 2017, where they observed 6 redshift 4.8 quasars. So 3 of them were individually detected by HERSCHEL, so pretty much like our own objects, and 3 of them did not have individual detection. So they were, if they were forming stars, it would be a much lower rates. Again, band 7 continuum at 0.3 arcsecond resolution, higher even than Bussmann, and found a 50% multiplicity rate. So 3 had companions, a distance between 2 and 7 arcseconds. This translates to something between 14 and 45 kiloparsec in physical distances, and 3 did not. Now, out of the 3 that had, 1 was individually detected by HERSCHEL and 2 were not. So therefore, if we want to compare with our sample, they say that 30% of the individually detected objects are multiple, which is pretty much what we also say. But of course, this is a bit higher redshift than ours and very, very small number statistic, but still it's indicative that, you know, we're not claiming things that are completely unfeasible, right? So, as I said, the ACA resolution is not optimal for such a work, but we wanted to see how much we can push our data. Okay, so what we did is we took, here I show just an example of 3, but we took the Bussmann data, resampled, and with our own beam. So there are 3 examples with separations between the 2 components of 3.5 arcseconds, 3 arcseconds, and 1 arcsecond, and with flux ratios between the primary and the secondary component of 1, 2, and 3. And after convolving with our beam, we saw these things, which means that our objects like that, we would have seen something like this in our images. We also did the same work with a single source, and this is what we got, and these are 2 of our own sources, right? So I think at first sight you can say that what we get is much closer to that than in fact this, right? I also ran some simulations with the ALMA simulation tool, so this is something that corresponds pretty much to the parameters of our own observations. So this is, again, a point source seen through a that looks like ours, in conditions that look like ours, in the declination that look like ours, and this is what we get. I showed before, and these are, we suspect, 2 objects separated by about 3.5 seconds, so something like that, but in the direction of the major of the beam. So in fact, what I'm very much tempted to say here is that unless there was some cosmic conspiracy whereby all our objects had companions within 1 or 2 arcseconds lying along the major axis of the beam, our sources are indeed individual and isolated. So I think they are really point sources and nothing is hiding in there. But there is, of course, this possibility that there is something very, very, very close that we will never be able to resolve. Having said that, despite the 4 arcsecond resolution, I think we can make stronger claims on the nature of these objects. Are these multiplicity arrays real? I'm going to say yes, they are, for at least the majority of the objects. So the question is whether these are chance associations, physically connected objects. So both Hodge et al. And Bussmann et al., they argue against chance associations based on simulated and real number counts. However, work by Cowley et al. Based on simulated observations suggests that, in fact, physically unassociated galaxies that contribute to a large fraction of these sources. So if we want to compare to our sample, which is about that brightness, according to these people, we would need about 5 to 8 individual sources to account for 95% of the 870 micron flux, which is, I think, quite unlikely. And these sources would be separated by redshifts of about 1. However, data tells us a completely different story. So this is a very recent paper that just appeared. So these people went and did spectroscopy of 11 sub-millimetre galaxies in 6 multi-component systems. And actually what they saw is that when the distance is, between the components is larger than 8 arc seconds, then it's chance association. So they have redshifts for these objects. When the distances are below, they are physically related with a very, very small redshift difference. So these are really merging systems. So again, this is small number statistics, but I think our objects compare quite a lot with this, because especially given that the separations between the various components are smaller than 8 arc seconds. So if they are, for the few objects that we found multiplicities, they are probably physically connected. So this brings me to the next question. Are major mergers triggers of concomitant accretion and star formation, not one or the other, but both together in the same system? There have been studies on this, in fact. So recently, Glickman et al. 2015, it was 15, not 9, that we were looking for yesterday, made a study of 11 dust-reddened type 1 quasars for the from the first bright quasar survey. So it means these are radio loud objects at redshift around 2, with very extremely high bolometric luminosities. So this is really the brightest quasars in the sky. And by modeling the PSF and subtracting it, they found traces of merging hosts in 8 out of the 11 systems. So they conclude that the luminous quasars and galaxies co-evolve through major mergers that trigger both star formation and supermassive black hole growth. This I took text off from their paper. However, I checked the paper. There's no work on the star formation, so I don't know. This star formation only appears in the abstract. So I think what they saw here is that very bright quasars can reside in major mergers, but I don't think that they can claim anything on star formation rate, but anyway. And they found that the components of the merging system were separated by typically 1 to 3 arc seconds. By the way, same work was done also earlier on by Tanya Urrutia and Mark Lacey with the same results. However, Mechtley et al. 2016 that actually went and imaged 19 unobscured quasars, so very similar to ours at redshift 2, again very similar to ours, and looked for distortions in their hosts. They found that there were very, very little evidence of quasars residing differentially into merging systems. So what they found was about 40% for quasars and 30% for inactive galaxies. The difference was not statistical. And the merger incidence did not correlate with any of the properties of the AGN, neither with the black hole nor with the Eddington ratio. So if systems are major mergers, they will certainly be post-coalescence, because there are really very little trace of merging in their system. But this sample is quite similar to ours, so I think this is something that we should keep in mind. So now back to our stuff. The redshifts at which our quasars reside correspond to angular distances of, so within the ACA beam of 35 by 20 kiloparsecs roughly. By degrading the Bussmann images, I think we were able to show that we can actually restrict this space even more. So we can say that if something resides within, in the vicinity of the AGN, that should be sitting within 10, 15 kiloparsec at most. And this means that if these systems are not unique, are not isolated, and have a companion, oops, what happened here? They must be beyond their first periodic passage, not only because of their distance, but also because the first periodic passage, the velocity is the highest, and then the probability of observing them is the lowest. So probably these are post-first passage systems. So this means that early stage mergers are excluded for the majority of the sample. Now, according to models, the peak of the global star formation rates in merging systems occurs a few mega years after the first passage, when the two objects are separated by a distance of between 10 and 100 kiloparsecs. Now, the AGN onsets after about 100 mega years according to models, right? And this is the time where the two components have approached one another. This is the time where the global star formation rate starts decreasing, and this is the time when the circumnuclear star formation is increasing, and this would probably lead to the correlation we're talking about between the star formation rate and the AGN correlation. And this is something we do not see in our sample again. So this is the luminosity at 870 micron. This takes into account the contribution of the AGN, so it has been removed. So this is really luminosity coming from the star formation. and this is the luminosity of the AGN, no correlation whatsoever. I know this is a very thin argument, but still this points against even late-stage mergers in our sample. So again, this points toward these objects being really, truly isolated. Now, I mentioned before we had 4 of the objects, single sources, so about 25% of them, that the ACA component was shifted with respect to the coordinates. And this most likely, for the and sub-millimetre doesn't come from the quasar itself, but from a companion that we do not see on the other images. If this is the case, this should mean, in fact, that the major merger fraction will increase, right? Because we have a few objects that are not seen simultaneously, but you have 2 objects next to each other, one forming stars, one this time, however, this could explain, at least partially, this lack of correlation between the star formation rate and the density in this sample, because the star formation and AGN come from different objects. There is no reason why they should correlate. We might have explained at least 25% of this mystery. So, do major mergers trigger the brightest AGN? Yes, at least part of them. So the only thing that remains to be answered now is, well, what happens with the rest? So, above 1,000 solar masses per year be produced by circular processes inside the host of bright AGN. Well, I'm not an expert at all on this, so this is stuff I dug out in the literature, but at redshifts 2 to 3, galaxies form thick gas-rich disks, and when this disk will merge, result in spheroids that are both gas-rich and luminosity. At the same time, the size of the galaxies of these redshifts is much smaller compared to what's happening in the local universe. So indeed, we can have very high star formation rates in compact objects that correspond to the redshifts of 2 to 4. We wanted to check whether there is at all any theoretical in our claims that yes, we need circular processes to light up these processes in objects. So we ran a realization of the analytical model of intergalactic medium and the galaxy, so AMIGA. This is a code developed by Eduard Salvatore Soler and Alberto Marique in the University of Barcelona. This is basically a model, it's a fully analytical, and they can trace back the progenitors of galaxies back to 5 generations based on a very complicated scheme. But the bottom line is that this model can reproduce the properties of the high redshift universe in an extraordinary manner. So we ran a realization, and in fact this was exactly the question we asked. Can we produce simultaneously high star formation rates, bright AGN, with circular processes at these redshifts? Well, the answer was this. So we found that the highest star formation rates in the brightest AGN occur at redshifts between 1.5 and 0.5, according to this model. And let me remind you of the characteristic of our sample that are very, very, very surprisingly similar to all these values. So there seemed to be also theoretical support behind, even though this is a work that we really need to go into the deeper details. It's just one realization of the model, but still is quite effective. So what we're doing now is really attacking all fronts. So recent ALMA cycle 6 deadline, we applied for a larger sample with ACA, we applied for much higher resolution and with a full array because we want to go and see whether indeed these objects are isolated. We applied with, for photometry with the William Herschel. We are planning to do HST follow-up for at least a subset of these objects. And actually, the reason why I'm currently physically here is because with Ismael and Rui, we're looking for the secondary counterparts on already existing data that are spread all over the world. So as an example, I want to show this one. This is an object that is offset. The ACA component is offset from the quasar. In fact, the quasar, we don't see it on the ACA image. This is what it looks on the WISE, 3.6 micron image. So this is a blend, obviously, of 2 sources. So here we can see both the ACA source and the quasar. And these are images Ismael dug out, deeper images with IRAC, where you can clearly separate these 2 things. We can also see the third counterpart here. So these are very, very important if we want to construct the SEDs of the secondary objects for which we have no information currently. This is another example. This is the blend I spoke about. And again, here it is very well resolved on these deep IRAC images. And finally, we're also looking for deeper optical data. Here, for example, we found the ACA counterparts, secondary counterparts on other data. So this is really what we really results from yesterday. Very, very fresh. Which brings me to the end of my talk. So if you are to take something away, I would say that, well, large fraction of optically and far infrared lasers have really single isolated millimeter counterparts, are at above 70%, be it from the object itself or from some companion, but they are single counterparts. We can exclude entirely for the vast majority example. Late stage mergers might be triggers of AGN, but not exclusively, and processes may indeed generate what we observe very star formation rates in very bright quasars, at least in these redshifts. So, thank you very much.
Evanthia, thank you very much for this very interesting talk. Questions?
Okay, thank you for the talk. In the previous slide, that triple source,
yeah,
could it be a lens?
Well, in principle, no. But these are typically the kind of things we have to check, right?
Yeah. So there's no spectra or anything?
No, for the time being, no. But it's, I would say it's unlikely, in fact. Because, okay, here it's not very well seen, but in fact, if you try to deconvolve the two, they still look like the beam. So it's, okay, it's really pushing it, but I don't think it is, no.
Okay.
Hello. You commented that the size of a black hole, or the mass of a supermassive black hole, has no relation with the star formation rate or something.
In this object, yes.
Yeah, in this object. The mass of a black hole has a relation with the luminosity of AGN? I don't know that.
So
is that common knowledge, or?
But the thing is that we're using the luminosity to derive the mass, right? Because usually, so for the majority of objects, the only information we have is the broad lines, right? Which correlate with the luminosity, blah, blah. So one correlates with the other, really. So for nearby objects where do a vibration or no, find out methods to measure the black hole, there you can say yes, the two indeed correlate.
Yeah, no, I'm asking, are there independent observations of the black hole mass and the luminosity AGM?
Not for this sample.
Okay,
it's impossible at this
no,
redshift.
but
yeah.
even for other sample, does it exist? Because in my simple understanding, the size of a black hole shouldn't be so important. It is more important the food of a black hole. I mean, in producing the AGM phenomenon. The size of a black hole may be above a certain threshold is enough to produce AGN. I don't know. I'm very ignorant. It's just
no. The thing is that, as I said, for very local objects, there are dependent methods of measuring black hole mass. But this is really for very local. You cannot go at this redshift and measure black hole. Yes. So these black holes are measured based on the luminosity and the broad line. So it's you know, it's a.
Is that an assumption, or is?
Well, we use this method because it has been proven robust in the local universe, where we have independent measures of the black hole.
More questions?
Maybe you mentioned it at the beginning, I forgot. Do you have an idea of what is the mass of the host galaxies, that are hosting the AGNs?
Well, we don't know, because these are type 1 quasars, so they are, they outshine the galaxy, so we don't have a means of measuring this. It's just that the fact that their star formation rates are so high, it places them above the main sequence, the galaxy main sequence. But this is pretty much all we can tell for now. And this is why we're after HST data, so we can actually observe, go for the host. Also, we don't have CO data, so there is no way to measure anything about the galaxy itself right now.
Okay.
What would be the limit in spatial resolution if you wanted to go to the highest possible ALMA?
Well, the highest possible with the highest band, so highest frequency, would be 0.004 seconds.
But I mean, for these objects, for this type of fluxes and so on, I mean, does it make sense to go a step farther and go to even higher resolution?
Well, I don't know. You should ask the cat, the tack, not me, because I mean, I think there's always interest in doing more and bigger, larger, more results and whatever. But you also have to weight the time with the outcome, right? So I think for the resolution we applied for, which is 0.2, which is about at this redshift 1 kiloparsec, I think this already will tell us enough about what's happening not only in the vicinity but also in the galaxy itself.
If I can comment something on this, so I'm part of the ALES survey of where you presented the Czechi's papers. So we're also going for a resolution of 0.1, 0.2, but it's clear that you have to be better than 0.3 to see better than 0.3 in arc seconds in the resolution.
Yeah.
Because due also to the multiplicity, not in large scales, but in smaller scales. So now I also have two questions. The first one is, did you also do smoothing of the ALES data to your resolution?
No, we did only the Boosman one, which was the highest resolution one. So yeah.
Yeah, but perhaps it also would be interesting because there the resolution was 1.5, so I don't know how many sources were within 4 arc seconds.
Well, it's something we can try. It's not very difficult to do.
And I have another question. So you, regarding especially the secondary components you have, did you think about to do the ultimative proof, CO spectroscopy? Also for example, also the guy you had before, which is offset of the quasar. So I also think it's linked, but to be 100% sure.
I did not put in a proposal because it would be a lot of time. And I wanted first to confirm the multiplicity before I go for this. And then we were also thinking that maybe there are other ways to obtain redshifts and stuff to, for the secondary components. So just,
More questions? Then if not, then let's thank again our speaker. And Ismail, she will be several weeks at the Institute. 2 weeks. And
Next week she's giving a talk at the museum. On Friday there will be another talk at the museum.